Some aircraft designs emerge into the light, serve for a decade or two, then recede into the historical record, perhaps re-emerging briefly from time to time to entertain airshow spectators. Others hit upon a fundamentally sound recipe, and then they keep getting re-engineered with new technological advances baked in each time. And then there is this third, most rarefied category. Designs that have seemingly been flying for longer than anyone can remember and are still doing useful jobs. Airframes built by the generation of our grandparents, serving as almost daily drivers for well over half a century sometimes. Like that perfectly weighted hammer that had already had a patina when we were children, but it sits so perfectly in one's hand that it still frequently comes out of the family toolbox. It's a very select club of aircraft types, this, and I'm sure we all have our favorite examples. Some of mine are the Douglas DC-3, the Antonov AN-2, the P-3 Orion, and the subject of today's video, the de Havilland DHC-1 Chipmunk.
With de Havilland's focus in post-war Britain firmly on the development of the world's first jet airliner, the mighty DH-106 Comet, the somewhat less glamorous task of designing a replacement for the RAF's 1930s era basic trainer, the DH-82 Tiger Moth, was assigned to the company's Canadian division. And this was the result, the DHC-1 Chipmunk. Over the coming years, nearly 1,300 examples would be built in Canada, the UK and Portugal, where multiple generations of pilots, including our reigning monarch, King Charles III, would get their first taste of aviation, courtesy of this elegant little trainer. Let us, in this video, take the back seat behind DHC enthusiast and custodian Captain Joe Brown, whose day job is to fly the National Flying Laboratory Centre's Saab 340 airliner featured in Design Deep Dive 1, and as we enjoy a gorgeous day above the fens, let us try and understand what has given this aircraft its extraordinary longevity. And here is the star of the show, Mr. Edward Moore's immaculately maintained Mark 22 Chipmunk, Whiskey Delta 310, with its recently rebuilt de Havilland Gypsy Major 10 Mark II engine, driving a Fairy Reed fixed-pitch aluminium propeller. After well over 12,000 hours of flying in its extraordinary 72-year service life to date, this ex-RAF example still looks absolutely spotless and resplendent, and it is now fully fueled and ready to go. As Joe completes the power checks before lining up and departing from an old Warden airfield, enjoying some rare November sunshine, it's a good time to try and sort of reverse engineer some of the performance foundations of the design of the DHC-1. Its takeoff and climb performance give us some clues as to the power plant choice and wing size of the aeroplane. Making some basic assumptions about the aerodynamic derivatives, the typical sea level ISA conditions Chipmunk ground run of just under 200 meters gives us a power required versus wing area required trade-off that looks a bit like this. It has a downward slope, of course, because trying to get away with a smaller wing would demand a more powerful engine, and vice versa. A typical field performance trade. Now, the sea level climb performance, about 900 feet per minute at an airspeed of 70 knots indicated, appears to be relatively insensitive to the wing area. However, the requirement to maintain just over 120 knots indicated in steady level flight at full power in sea level ISA conditions, as well as the requirement for the Chipmunk to still be climbing at 100 feet per minute at about 15,000 feet, about as high a service ceiling as one might ever need in an unpressurized cabin with no supplemental oxygen, translate into power required curves with a positive gradient. That is, the more wing you have, the more power you'll need. This is true of the sustained turn rate constraint as well. All of which, if my back-of-the-envelope arithmetic is correct here, seem to suggest why the Chipmunk ended up precisely with its 16 meters squared wing area, with the Gypsy Major engine sitting neatly in this lowest power dip, resulting between the competing constraints of field performance versus everything else. Incidentally, over the decades, many pilots decided to rip up this constraint diagram and draw a much more aggressive one. Perhaps no one doing this quite as emphatically as the great stunt pilot Art Scholl, who nearly doubled the power of his by fitting a Lycoming 0435, while at the same time cutting the wing area. He also removed all excess weight, such as one of the seats, and fitted a retractable undercarriage. With probably close to half the zero-lift drag and double the power, this 1947 built Chipmunk, now on display in the Smithsonian's Udvar-Hazy Center, was probably in need of a new set of performance charts. In any case, back to our classic Chippy. It would be ideal at this point for us to have another Chipmunk around to help us point out some of the key features of the airframe, but that would be too much to... Oh, but would you look at that? In a case of complete and utter coincidence, we have just stumbled upon one in the skies of Bedfordshire. Pilot Ben Griffiths, kindly supplying the illustrative item this morning, describes Gulf Oscar as a working aeroplane, not a spotless museum exhibit, but it certainly cuts a very elegant figure in the morning sunshine. This is a UK-built ex-Army Air Corps example, and it does wear an Army livery. So, with a leap of imagination, let us start from the front. The shape of the nacelle and the asymmetrical intake generally follow what one might call the de Havilland house style of the era, seen as early as the 30s on the also Gypsy Major powered Tiger Moth and the Dragon, the Gypsy 6 powered Rapide, and then as late as the 50s, ×4 on the Gypsy Queen powered Heron. The airframe has a stressed skin, mostly aluminium alloy construction, with a low cantilever wing. It is a tapered wing with a straight leading edge and a straight trailing edge, the entire length of the latter being divided between inboard slotted flaps, more on which shortly, and outboard ailerons. The wingtips are of the rounded variety, showing half an aerofoil profile in the planform view. Since the seminal work of Sieghart Herner in the 60s, we don't see this shape very often, although what it lacks in terms of induced drag reduction potential, it essentially decreases the apparent aspect ratio, it might make up for in some cases in terms of ease of manufacture. The fuselage is long and slender, obviously good news from a pressure drag point of view. This was made possible by the choice of the Gypsy Major with its 4 inline cylinders. Compare the Chipmunk, for example, to its contemporary, the much stubbier North American T-28 Trojan trainer, powered by a Wright Cyclone radial, or its predecessor, the 1930s North American T-6 Harvard, powered by an enormous Pratt & Whitney Wasp radial. An aircraft that, incidentally, was used by the RAF before the arrival of the DHC-1. Just before we let Ben peel off into the distance, let's have a closer look at the aerodynamic design of these wings. The outer mold line is a loft between two well-known profiles. At spanwise station 80, this is about 38% semi-span, we have a NACA 2415 profile. So we have a camber of 2% of chord at the 40% chordwise station and a maximum thickness to chord ratio of 15%. At spanwise station 190, this is about 10% short of the tip, we have a USA 35B profile, known from some early Pipers, the Cub, the PA-23, and so on. I have the leading edges and trailing edges lined up here to show that this is thinner, but has about twice the camber of the 2415, picking at roughly the same chordwise station. I suspect de Havilland were aiming to select aerofoils such that they achieved the same effect as washout normally does, avoid the tip stalling first, but without the manufacturing awkwardness of twist. What wind tunnel data might have they been looking at? The first edition of the Abbott and von Dönhoff fundamental tome on the theory of wing sections postdates the design of the Chipmunk by a little, but this NACA data on the 2415 will no doubt have already been available and might have made it a good choice. There are several Reynolds numbers here, with the highlighted one, the most relevant to the DHC-1, as it was measured at about 3 million. This is the low end of the Chipmunk speed range. The lift curve we see here maxes out at 14 degrees, with a relatively sharp drop-off. Now, the choice of the outboard section is a bit more intriguing. The USA 35B has a camber of 4.1% at the 40% chord station, and it is 12% thick, being actually very similar to the NACA 4412. I couldn't find 1940s public domain data on the latter, but there is a 1925 report packed with these beautiful blue plots of wind tunnel lift and pitching moment curves on a range of similar aerofoils, including the USA 35B, featuring a nice, relatively robust-looking CL peak at an alpha of 15 degrees, so 1 degree beyond the 2415, exhibiting a maximum lift coefficient of 1.37, which places it in the leading pack in this 1925 comparison, at a Reynolds number of 3.6 million. At the same time, its minimum drag coefficient is the best of this top 5, at 90 counts. So here is what I suspect happened here. De Havilland needed to fit 9 imperial gallons, about 41 litres of fuel, into this space, each side between the leading edge and the spar, setting the first thickness to chord ratio constraint. The other came, presumably, from the spar depth required to carry the estimated mass of the aeroplane, times 6 at the limit, more on which in due course. And this will have resulted in about 15% of the just under 2 meter chord at that point. And the rather well understood NACA 2415 was thus a natural choice here. Outboard, well, the spar depth requirement may have set the thickness here again to about 12%, at which point the NACA 4412 would have been a good fit, but with no extensive wind tunnel data available, The USA 35B, rather well known and well understood, may have seemed like a solid, safe alternative, especially with its likely higher critical alpha, promising stores without the sort of wing drop that may not have been desirable on a basic trainer. Now, what does all this amount to in terms of the lift curve of the 3D wing? Well, we know that the zero lift alpha of the wing is likely to be between the zero lift alphas of the two sections. What about its slope? De Havilland's engineers will have seen a wartime German paper by Helmbold, whose lift curve slope model, shown here in its form refined by Nacker's eddy polymers to account for swept wings, gives us 4.4 per radian. As expected, this is considerably shallower than the 2D profiles, which are closer to the 2 pi predicted by thin aerofoil theory. So where is the CR max of the 3D wing? The best indication we have for this is the placarded 1g store speed of the aeroplane at the maximum takeoff weight. This is an indicated airspeed, as sensed by the DHC-1's rather substantial pitot tube out near the port wingtip. Through some relatively complicated plumbing, this is connected to airspeed indicators in both cockpits, with the static pressure also seen by the rate of climb indicator and the altimeter in each cockpit. The system works really well at high speeds, but in spite of the pitot tube being quite far outboard and a long way off the underside of the wing, it underreads by over 10% at speeds close to stall, power off. So a clean 47 knots indicated airspeed is likely to be around 53 knots calibrated. Though this is literally off the chart provided for calibration, so we're having to extrapolate a little. This, combined with the fact that some frantic hand waving is required to leap from this placarded, calibrated stall CL to an aerodynamic CL max, means that the resulting estimate is probably best taken as merely a practically useful number rather than precise aerodynamics, not to mention that we're also neglecting the contribution of the tail at this point. At any rate, this all works out to a critical alpha of about 17 degrees, with the pilots experiencing about 15 of those degrees around the stall buffet. The wing is set at 2 degrees. Of course, this means that the pitot tube is also facing away from the free stream by 17 degrees, which may be partly to blame for the positioning error. As we turn onto the approach to land, it's a good time to contemplate the Chipmunk's hand-operated single-slotted flaps. The approach is flown at 60 knots indicated, with the flaps deployed at either 15 or 30 degrees, better visibility over the nose with the latter and a shorter ground roll. Each stage of flap nudges the lift curve upwards by about 15%, with enough margin here for the handbook to simply specify 55 knots indicated at the flare, regardless of weight. The book also quotes a single landing distance of 434 meters from a 50-foot screen height. The rollout is quoted at 155 meters with the use of brakes, presumably assuming max weight. The final after-landing checklist item is to admire the gorgeous lines of the aeroplane in the late autumn sunshine. With pilot refueled, it's time to fly once again. This time we're also joined by pilot Carol at the controls of another beautifully looked after 1950 built Chipmunk, wearing the silver RAF livery with yellow bands. What a privilege it is to be hanging out this afternoon in formation with these lovely reminders of Britain's and Canada's aeronautical heritage. With over 700 examples, the RAF was by far the most significant operator of the Chipmunk. In its training role, the DHC-1 served the UK's armed forces, also serving for the Army and the Royal Navy, from 1950 to the early 90s, operating RAF air experience flights until 1996. In actual fact, 2 chippies are still in service with a Battle of Britain memorial flight. Not displayed much, but used to train their pilots in tail dragger flying in preparation for flying the BBMF's Hurricanes and Spitfires, as well as for a variety of utility roles like the reconnaissance of new airfields or for ferrying spare parts for the rest of their fleet. Incidentally, the little silver model I was waving around in intro represents one of these BBMF chippies, Whiskey Kilo 518. The Chipmunk had numerous licensees and export customers too, most of which have also now retired them from active service, with one notable exception. The Portuguese Air Force still operates the DHC-1 in its Academia da Força Aérea. Its 802 squadron is the entry point to all pilots to go on to serve in the Portuguese Air Force. The key difference compared to the aircraft in our formation is that these are powered by the 180 horsepower Lycoming 0360. The sun is close to the horizon as we wave goodbye to Carol and Ben, but Joe isn't quite done putting the chippy through its paces. The calm evening offers an ideal opportunity to observe the flight dynamics of the DHC-1. Here Joe is demonstrating the phugoid, the longer period longitudinal oscillation of the aircraft. In response to a speed disturbance, the aircraft goes through slow, damped cycles of converting potential energy into kinetic and back. Look, no hands, says Joe. Oscillating between low speed, low G peaks and high speed, high G troughs. All this at an essentially constant angle of attack and with gradually converging oscillation amplitudes in all variables. In a roughly minute-long period, we cover about 800 feet of altitude range with a speed cycle amplitude of about 50 knots and the engine RPM following along, varying in a range of about 500 RPM, all fairly typical of a light prop. With both the self-loading ballast in P2 and pilot up front enjoying the golden hour light above Bedfordshire, Joe decided to give me a taste of the aerobatic capabilities of the Chipmunk. As the ground and the sky swap places and then reoccupy their more customary positions after this barrel roll, let us consider what the aerobatic limits of this late 1940s ex-RAF trainer actually are, by attempting to reconstruct what its design flight envelope may have been. We're going to draw this in the usual way into the load factor, that is the lift-to-weight ratio, versus equivalent airspeed space. Let's start with the gust loads. Perhaps the most authentic starting point in this reverse engineering attempt is the US Department of Commerce Civil Aeronautics Manual 1944 edition. This is a sort of acceptable means of compliance document, as we would call it today, fleshing out the calculations required to satisfy the actual requirements, and copies of it were no doubt lying around on the desks of de Havilland's engineers in mid-1940s Canada. There is nothing earth-shattering, even through modern eyes, in how this deals with gust loads, the focus being the usual 4 conditions: positive and negative gusts at positive high and low angles of attack, giving us a 30 foot per second upward gust at high alpha and a 15 foot per second upward gust at the design dive speed, plus the same for downward gusts and negative alphas. What is a bit more unusual from today's perspective is that gusts are treated as sharp-edged. The DHC-1 predates the advent of 1 minus cosine and all that. Though the document references, without giving much by way of a reasoning, a basic wing loading dependent gust alleviation factor of sorts. Putting all this together and inserting the lift curve slope we found earlier, the gust lines end up looking like this. Joining the dots as per the 1944 manual, we end up with a best guess of what the design gust envelope of the Chipmunk would have looked like. Assuming a design dive speed of 200 knots, kind of hard to guess what that value will actually have been, but it doesn't make much of a difference. In terms of maneuvering loads, we can take the CR max we estimated earlier and draw the two accelerated stall curves. De Havilland wanted an aeroplane suitable for training future Spitfire pilots, so the positive one would likely have been drawn to 6G. The airworthiness requirements document prescribed a general positive maneuvering load factor increment of 3.5G for the weight and power loading of the Chipmunk, so a limit load of 4.5G, which is where we can close the envelope. Applying the usual ultimate load factor of 1.5, we get the "there be dragons there" range of possible permanent airframe damage, followed by the "I hope you brought a parachute, although you've G-locked by now anyway, so it doesn't really matter" domain. Now, a very important note, much of this is rendered somewhat academic by a string of additional restrictions. First, the manual has a never exceed speed of 155 knots. Incidentally, this was originally 173. There is also a handbook maneuvering speed at the seemingly relatively conservative 117 knots. There is also a restriction on sustained inverted flight, which I suppose is somewhat ironic on an aircraft equipped with an inverted engine, but it's not that surprising or unusual. The Gypsy Major is simply not equipped with a negative G fuel and lubrication system. This is obviously a significant limitation in terms of aerobatic flight, and combined with other oversights, such as not having sufficient room to recover in case of mid-maneuver fuel starvation, can have potentially disastrous consequences, as seen in this NTSB report. In terms of further restrictions, the manual makes it clear that the DHC-1 isn't really a 6G aeroplane, or rather that the frontiers of the envelope should never be visited intentionally. Though quite what staying well below 6G means is not completely obvious, but it does take a further bite out of the flight envelope. So, what does all this mean in terms of aerobatic flight? For a start, it isn't permitted, unless the aircraft has a particular modification, dated 1958, a pair of anti-spin strakes. These were added to UK and Portuguese Chipmunks following a number of accidents, and the observation that, to quote an AIB report, the Chipmunk displayed its own individual characteristics when being spun, which included an occasional tendency to perform as many as 3.5 turns from the time recovery was initiated until it was completed. When these are fitted, tight turns, loops, slow rolls, etc., and even spins are permitted today. Spins and strakes have always been a somewhat contentious subject in the world of the DHC-1. In fact, the Australian Department of Civil Aviation dedicated a lengthy report to the subject, published in the 1960 Safety Digest. It reports on an extensive analysis by de Havilland themselves of spins conducted in close to 1,000 chipmunks in normal and extreme COG conditions. These were, by the way, original strakeless chipmunks. And notes that none of these aircraft failed to recover or caused concern. More interesting still is that this document comments that the manufacturer also experimented with the fitting of fuselage strakes to ascertain if they would reduce recovery time. To summarize their conclusions, only in the order of 3/4 of a turn in the worst case. Which does raise a few questions, amongst which, how many experiments would you have to do? And how many aircraft with and without strakes before you could draw a statistically significant conclusion like this. In any case, the Australians did their own extensive experimental investigation and concluded that the department has no hesitation in declaring its complete confidence in the spinning and recovery characteristics of the Chipmunk and fully endorses the techniques prescribed by the manufacturer. Incidentally, the Chipmunk's contemporary competitor, the Percival Prentice, which designed for the same role as the DHC-1 and beat it to a first flight by a few weeks, also had its share of spin-related dramas early on, as well as anti-spin strakes. In fact, it was in serious trouble, as recalled by the late great Eric Winkelbrown, who was called in to troubleshoot the issue that had already claimed lives. At this point, there rarely are, of course, any easy fixes, and the Prentice required a rather significant set of design changes. If you are suddenly more aware of the wind noise of the airframe than in previous clips in this video, that is because Joe is simulating an engine failure on our way home, to the extent of throttling back to flight idle for the approach at around 1000 RPM. For added excitement, we are also flying a Spitfire-style curved approach into Old Warden, a useful skill for any pilot, especially for one flying an aircraft with a long nose that obscures the view of the runway. It is a technique that may also be needed around airfields surrounded by high terrain or for noise abatement reasons. And there's the reassuring hum of the Gypsy Major coming back to life as Joe executes a touch and go with a quick circuit and another curved approach concluding our adventures in the Chipmunk. I hope this has given you a taste of this rather lovely machine, a somewhat unglamorous workhorse, but one that has touched the lives and careers of more pilots, certainly in the RAF, than perhaps any other type. If you are one of those, or you still fly or work on a DHC-1, do share your impressions and recollections of the Chippy in the comments. Thanks for watching.